All right, this is a recording for the paper Feb March to 1, paper 42, question 8. If you have yet to try the paper, and if you are watching this in preparation for your A2 paper coming very soon, please try the paper first to see how you fare and then come back. The video is here, it's not going to go anywhere, and you can try the questions. All right. So here, question 8, we have two long straight wires, P and Q, and they are parallel to each other. Very familiar. All right, there's a current in each wire in the direction shown. The pattern of the magnetic field in the plane normal to the wire due to the current is also shown. Okay, very nice. Normally, they will ask you to draw the circle. Now they draw for you. Oi. Part 1. Draw arrows on the magnetic field lines around wire P to show the direction of the field. So it is time for us to use the right hand, the correct hand, which is the right hand grip rule. So let me pull out a picture so you can see how the right hand grip rule looks like. Ding, ding, ding. Okay, it's going to look like this. Okay, so you have a hand, and hopefully your hand looks like mine. Unless you're an alien, then welcome to Earth. Why do you come now? It's COVID-19. Are you coming to help us? Right, anyway, your hand is going to be pointing up, your thumb is pointing up, because the direction of current is pointing up. This one is your eye. This is your eye, right? And you look at your finger, they are curling anti-clockwise. So make sure when they say draw arrows, you draw more than one lah. Like that. I think this is good enough as a teacher. I'm happy with this, but if you are not, then you draw another one. No. But if you draw more, please make sure they don't contradict each other, okay? Make sure that they are moving in the same circle. Don't draw like this and then for some reason draw this way and then I am confusion. Alright. Okay, so... okay lah, it's good enough. It's more than enough. In fact, I think it's too much. This is good. Alright. Determine the direction of force on wire Q due to the magnetic force from wire P. Okay, it's time to take out your Fleming's left hand. If you are struggling with this and you want a proper view of the wire, please watch the video recorded in the playlist after this, okay? Because if I'm going to use my left hand here, I'm not sure whether the image is flipped and I'm kind of tiny and I have to adjust all the settings, so I'm not going to do that. Use your Fleming's left hand and you think about the magnetic field in this point. So if I extend to here, it means that the magnetic field is actually going into the plane of the paper. Okay, into your screen. Into this point, this one. So if it's into, then I'm going to draw a cross. This is the direction of B. Okay, going into direction of B. This is the front view, which makes it easier to use your left hand. So we go FBI again. Okay, if you're using FBI, your middle finger is your magnetic field. No, middle finger is current. So point your middle finger out, not in a rude way, but point your middle finger up. And then your B is going inside the paper. So you will find your thumb is pointing to the left. Okay, middle finger is up. Please don't demonetize me, joking. Okay, and then the B is going inside. So FBI. If you need a very clear view, we have those. They are already recorded. Okay, so this one, you will see that this is to the left, like Beyonce. This is F. You know, determine the direction, we gotta write it down. So, to the left, towards wire P. Okay. The current in wire Q is less than the current in wire P. Okay. Wow, this one is very common. Whenever I say parallel wire, I have gone to expect this question. State and explain whether the magnitude of the force on wire P is less than, equal to, or greater than the magnitude of force on wire Q. So when they say state and explain, you can just tell me whether the force is equal, larger, or smaller than, and then you can explain why. So we'll do that. I'll start by saying that the magnitude of the forces on both wires are equal. Okay, and the reason why they're equal is because the force between these two wires is equal to BIL sine theta, but theta is 90 degrees. Okay, pay the bill. But this B, let's say this B is from this current I1. So by the time you reach here, there is B1. I can say B1 is proportional to I1. The bigger the current, the stronger the field here. Right? Bigger current, stronger field. I2 is this current, I2. The magnetic force is proportional to I2. See? But if I bring it together, I can say the magnetic force is proportional to B1 and proportional to I2. So the force is actually proportional to I1 times I2. Or in normal English, the larger this purple current, the larger this purple field. The larger the purple field, the larger the force. The larger the green current, the larger the force. So if we are going to multiply them because they both make the force larger, then it means that it doesn't matter whether it's 2 times 6 or 6 times 2. All right. If you want to see the derivation of the equation of force per unit length, which is mu naught I1 I2 over 2r, 2 pi r, where r is the distance between the wire, please go watch the video. It's already recorded. Okay, so at this point in time, exam is either you know this or you have to logic out in your head slowly. So this is why I say the magnitude of force on both wires are equal. Okay, the easiest way to explain is because the force on both wires are proportional to the product of two currents. This is one way you can explain it. Okay, so we have already drawn the force on wire 2. Wire 2 will attract this way. Miss, can I repeat the process for wire 1? Sure. If you do wire 1, right hand grip rule, on the left side of wire 1, your finger is pointing towards your face. So for wire 1, right, the field will be coming out. So this is the field of wire 1. This one. This is the field of wire 1. B2 is pointing out. So if this B2 is pointing out and you do the whole FBI thing again, where your middle finger is pointing outwards, but your index finger is pointing towards your face, which will look something like this. It's kind of hard for me to do with the camera front facing, but you will still find the force to be in this direction. These two wires will attract each other. Means they look suspiciously like Newton's third law. You are right. So this one can be example of explanation 1. Explanation 1. Or explanation 2, we can use Newton's third law. All right. So what we can say is the force on wire 1, wire P, wire P is equal in magnitude to the force in wire Q, since both forces are an action-reaction pair according to Newton's law, Newton's third law. Okay, you can also add the conditions of Newton's third law. I just have to write a bit more. They are opposite in direction, and acting on different wires or different bodies. So if you think about your AS, your Newton's third law have 4 conditions. 1, equal in magnitude. 2, opposite in direction. 3, acting on different bodies. And the fourth one, it must be the same type of forces, but this one no need to mention lah, they are both magnetic force. Okay? And I think this is a bit harder to write because, okay, this is based on past year mark scheme, okay? I think this is harder to write because based on past year mark scheme, they were not explicit about how detailed they want you to be. They just say correct application of Newton's third law to forces. So if I'm an examiner, it depends on how strict I want to be. I may want to see all 4 of Newton's third law properties explained clearly, and then you say same magnitude. Or you could say force or force per unit length is proportional to the product of 2 current, and then same magnitude. So I prefer to talk about the first one, equation easy to explain, okay? But provided you know the equation, or if not, you just take your time to write about Newton's third law. Equal in magnitude, opposite in direction, their action-reaction pair. Personally, if I'm marking, I am satisfied if the candidate mentions that they are equal in magnitude and opposite in direction, and also tell me that they are using Newton's third law. Okay, but they may want you to talk about acting on different bodies and same type of force. So minimum, you should be able to mention that they are equal in magnitude. And then this one, you see, opposite in direction. All right. Okay, anything else? Oh, there's part B. Okay, so this one is a force on a conductor. Don't forget to also study the force on the moving charge. Okay, so look at examples involving magnetic force on conductor, straight conductor. We also have magnetic force on moving charge, which is your velocity selector and your turn, your charge turning or charge deflection. Check out the playlist. Too much to talk about. Go and watch the playlist. Part B. MRI is used to obtain diagnostic information. I'm sure, of course, they're gonna put in some MRI somewhere, right? Or some medical physics. Okay, radio wave, right, are produced and directed towards the body. Radio wave affects the protons or the hydrogen nuclei within the body. Explain why we use radio wave and why the radio wave is applied in pulses. So when it comes to MRI, right, it's a pretty long story about using magnets to disturb the hydrogen nuclei in your body and using that to be able to produce images. We have recorded a pretty long example video here, which talks about how the MRI works. So it goes from everything from precession to resonance to relaxation. Okay, precession, resonance, relaxation. And this radio frequency focuses on the relaxation part. So go and watch the video because sometimes they could ask you to explain the entire MRI in 8 marks. Okay, all right. But this one, they only ask radio wave. I like this kind of question. 2 marks, 2 marks. All right. So why do we use radio wave? So once we precess means we make the hydrogen or the protons to be arranged in a particular fashion. Okay, we force them to be at a particular angle. So once it is precessed, right, or it arranges itself along the large magnetic field. Wait, let me paste this. Whoops. Why can I paste? And is my computer okay? Hang on. Technical issue. Why? Okay, so here is what is happening to your hydrogen nuclei. So like normal people, if I got picture, it's easier to memorize lah. First, you have a large magnetic field, right? And your large magnetic field will cause the hydrogen nuclei to precess. Okay lah, you know what? Let's just very quickly go through the important steps, but not the keywords. Okay, so we precess first, meaning we force the hydrogen to rearrange itself. Like this. Okay, so this is called precession. From here to here, the rearrangement, like funeral precession. At least that's what I think about. You arrange ma. Okay, so this precession, how do we do it? We use large uniform magnetic field. We make everybody arrange itself. And then what do? We send in radio frequency. We send in radio frequency so that this hydrogen will get excited and flip into high energy state by absorbing the radio frequency pulse. Radio frequency is electromagnetic radiation. It is still a photon. So I will say we use radio wave, okay, because its frequency is the same as the natural frequency of precession. The natural frequency of the hydrogen or the precessing protons. They call it protons ma, okay lo, but I normally like to call it hydrogen nuclei, but sure. Known as, I'm not sure how to pronounce this name, I hope I'm pronouncing correctly, Larmor frequency. Okay, so it has the frequency that's same as the natural frequency as the precessing proton, known as Larmor frequency. This means that your proton absorbs the energy and flip into high energy state. Known as resonance lah. Same as natural frequency ma. The radio wave is your force frequency. So if I am going to write a mark scheme, if I'm suggested only, okay, we don't have the mark scheme. So you mentioning that the frequency of radio wave is same as the natural frequency of the precessing proton or the Larmor frequency, this is B1. Okay, and then the other mark will be where you say the protons will absorb energy and flip into high energy state. This is B1, known as resonance. Okay, but why don't we just keep applying radio wave? So here is, this one is excitation. We put radio frequency so that it can excite. Resonance. Why do we put pulses? Because when we excite, you can't stay high energy forever, right? You will finally relax into a low energy state. So I don't want the hydrogen to be at high energy forever. I want to give it time to relax. And depending on how quickly it relaxes, I can know the type of molecule or the type of body structure that is inside, that this hydrogen nuclei is inside. So different stuff will have different relaxation time. See, water will have a relaxation time of a very large relaxation time. Fat will not. So depending on where this hydrogen proton is inside your body, I can actually build up an image of how your body looks like on the inside, hence medical imaging. So I need to measure the relaxation time. That's why we send things in pulses. So when it is excited, it will go to high energy. When it comes back down, it will release back the radio frequency pulse. That is the time between detection and receiving. I mean, between pulsing and detection is your relaxation time. And we want to measure that because it depends on the type of tissue that it is in. So let's say this is T1, I send the pulse in, and then by the time the detector receives the pulse T2, the time interval T2 minus T1 is what we want to measure, this one. Let me compare with this one. Okay, so if we don't send pulses, it will keep being excited, which is not what we want. We want it to relax and give us back the pulse so we can measure the time. So we're going to write that in, or try to write it in 3 lines. Okay, so what we can say is that the pulses, okay, so that it allows the proton to relax or undergo relaxation into lower energy state, releasing a radio frequency pulse, or emitting a radio frequency pulse. Time interval between the end of incident radio wave and emitted radio wave is measured or detected for imaging and process. Whenever you see process in medical physics, this means to form picture. You have to understand, in the generation of the people who wrote this textbook, they have to process their photos. You know, it's not the time of TikTok. They actually need to take the photo and put it on a film and send to a shop to process, or put it in some chemicals. So that's why they use the word processed. So we detect the time interval, and we use information on the time interval to tell what tissue it's in: fat, water, etc., etc. All right, that's it for Feb March for 2-1, paper 4-2, the magnetic field question.